Hi, my name's Steve Downey. I'm with Bloomberg. I'm the principal author for the paper that finally got stood optional over references into the standard. So we'll be talking today about what we got in, why it took so long, and what we expect to get out of this, and what we don't expect to get out of this, and a bunch of things that we still need to do, some with optional and some with other parts of the standard. Title slides, so I don't accidentally lose the title slides. Software used for preparation here. Intent is that this should be accessible, legible. It's like for everyone, good contrast with colors, etc. So standardizing optional over references. Optionals were first proposed in 2005. Optional over a value we got in 2017. Optionals for lvalue references were voted in at the Sophia meeting in June. The original proposals for optionals with references, or for optionals, had reference semantics, which were pretty much what we've ended up with. Why this takes so long? Considering that everyone was well-meaning and had good reasons for disagreeing over what they thought should be going on. So it's like, we had Boost.Optional coming in with the reference semantics that it has today. There was a proposal that made it pretty far for C++20, which was not adopted. And then, fortunately, Jean-Hid Menez, who is now the editor of the C standard, after getting frustrated over not getting optional over references, did all the archaeological research to find out what things had actually been done and what were the competing reasons for things being done certain ways. That led directly to my paper, which is we should just do this thing. And then, of course, it turned out there were far more details than I'd thought that there would be. So why so long? It's like, how did we address concerns? It's like, what did we end up with? What remains to be done? Core problems is basically reference semantics for a language reference. They're weird. References do roughly 3 entirely different things in the language. They define a calling convention semantic. You pass by reference, great for things like operators where you want to just operate on things, or by not making a copy for the thing that you want. The other extremely useful thing is giving some expression a local alias, which ends up taking no space. The compiler just says, oh, you've given this thing a name. That this dot that dot the other thing, arrow, even something further out there. You give it a name, the compiler's like, good, I will keep track of that for you. It's just an alias. And then we can put a reference in a struct. And that's complicated and terrible. If you've ever put a reference in a struct and suddenly you lose all your special member functions, all the default things no longer work, it's because references are strange. It's like the fact that we can't reassign them is like very useful when you're treating it as an alias. Doesn't come up when you're treating it as a calling convention. When it's an object in a struct, which is going to take up space, it's peculiar. So there was a lot of strong theoretical justification, like, okay, well then an optional with a reference in it should act like a struct. It's like it should have a reference member, and once you bind it, you're done, right? Except no one really likes that semantic. It turns out to have a lot of additional problems, but it's well motivated. That it's like we'd like optional of holding a reference to act like a struct with a reference in it. This argument goes under the banner of assign through or rebind. With assign through being like just pass through and go to the underlying, or do we rebind on an assignment from a T and make this thing refer to something else? And if it's actually a reference, well, you can't do that. The key observation that Jean-Hid made, both through his own library and doing a lot of the research, if you make it state dependent of what happens in an assignment, if assigning to an optional that's disengaged behaves differently than an optional that's engaged, we cannot reason about it. This is provable. We have all the bugs that anyone who's tried to do this has created. If you have to reason about the dynamic path your program took to figure out what it does, you won't. And that you want to be able to reason about what your program does by just looking locally at the code. So what we've ended up with is that optional over a reference just has a pointer inside it. We constrain a lot of things about that pointer, but it's just a pointer. This also has some other issues with it. So let's just do a quick overview of what an optional of just a T is. It's an owning type. There's an object in there, and there's one. And this is a value semantic type. You can copy it. You can do everything. Anything that the underlying type lets you do, you can do with your optional T. It just has one extra bit of information that there might be nothing there. So this is useful if you don't otherwise have like an out-of-band value. So it's like you don't have a way of expressing EOF because you don't have an extra value to say this is out of band. It's like, I get one extra value from this, and that's the one that there isn't actually a T in the optional. But very useful, and yes, this is what nullable pointers act like also. That null value for the pointer where it's like, oh, we've got an extra bit of information. It's because 0 is otherwise not a valid address. Sometimes there are architectures, but it's algebraically, it's T plus 1. There's one extra value. There's everything that you can do with the T plus one extra thing. Logically, it's a stud variant of T and stud monostate. Not actually implemented this way, but this is also important to keep in mind because a big part of the long discussions about how to do this for optionals are actually proxies for what we really want to do with algebraic types like variant and expected and a lot of other things. But we ended up having the argument over optional first. This is part of what's now we can start doing the rest of that now that we've figured out what the semantics that we'd like when we say we want reference semantics are. So the core use case for an optional is like, I'm reading from a config file, it might be there or not. And it's like, this gives me a better way of modeling this in the code. I'm less likely to forget how things, the case where the optional is disengaged because it's staring at me right there as being an optional. With C++26, we can use this cute bit of syntax. The syntax is a little bit controversial only because people aren't used to it. But this iterates over, optionals now a range. It's not a container, because container has a long list of things that it has to support. Ranges just have to do begin and end. Begin and end for an optional, it's like, if it's engaged, you get a pointer to it, and end is one past the end. If it's disengaged, you just get the end pointer. So, and this will iterate over the optional either 0 or 1 times. The nice thing about it is that if you know that if you're in the body of the loop, you definitely have a value, and you don't have to worry about it after that. Not a big deal on slideware, where you've only got 1, 2, 3 lines of code. I know in my own production business logic code, there are big chunks of code where I have to go back and look to see if I've actually checked if something is null or engaged or not. It's like having the optional, it's like with something like this, where I never get in, it's a little easier to read and reason about locally. The other important use case for optionals is a default optional parameter. This is useful, but it's also one of the reasons that optional is so complicated, because we want to be able to use it interchangeably with the underlying type or things that are convertible to the type that we've got in our optional. So you can say that I have a default parameter of an optional int, and by default, it's disengaged. But you can pass me an int, it'll get promoted to the optional int. This adds a whole bunch of constructors and a whole bunch of conversions that make it challenging to implement correctly and not have any surprises. We're not good at reasoning about overload sets. There might be a couple of people in here who are, but in general, like our normal instinct is, it's like, if it's this, it's over here. If it's here, it's like we go off on this side of the decision tree. The compiler just looks at the whole thing as a set at once and finds the best match according to the rules, and that can be surprising sometimes. But here it's like we're using the default optional parameter. It's like call the same function with just 1 int or with 2 ints, and works as expected. It's a nice convenience feature when you're working with optional arguments. Okay, quick overview of optional tref. Like what we generally want for it without getting into a lot of the details, but it's a non-owning type. Like there isn't any value inside the optional, it's referring to something somewhere. It has reference and value semantics, which is pointer-like. Pointers are good values. You can copy them, you can compare them, they've got their own identity, but they also can be dereferenced. They have reference semantics, and that's what we want for an optional tref. And they have one additional value representing the empty state, and we've essentially mandated the core optimization that that's the null pointer inside the optional. There's no extra space for extra bits that we need for this. Core use case, looking up something for modification. It's like, so today, you've got a map, you find things in it, and this is unsatisfying. You always have to deal with first and second for the because the iterator, the reference type for a map is a pair of the key and value, and if you just want the value, you've got to write second or first or something, and it's noise. You don't. It's like what we'd like is to just return an optional int ref, for example, and it's like We still have to check if we got one or not. But the code's a little more straightforward in terms of being more likely to be correct. There's some, the fact that it's an optional hints that you ought to check to see if you found the thing. And also, since it's a reference, we can mutate that value. So you've got your collection of people, enemies in the game, and you can change their state in them and do the kinds of things that you'd like to do without having to deal with pointers per se. There's also some utility for them as a optional reference parameter. Instead of a pointer, pointers have way too many possible semantics. Describing like this logger as an optional tells you that the thing that's receiving it is not going to like try and delete it or do something else to it other than it's going to, you expect it to be valid after the function returns. It's like clear implicit contract, as clear as implicit ever is. And by passing it as an optional parameter, it's like if someone doesn't pass you a logger, you can just skip over the logging part, for example. It's not a great dependency injection framework, but it's kind of a minimal dependency injection framework. I've yet to see a really good C++ dependency injection framework. There's trade-offs that it's like, I don't believe it's impossible, but there are some language proposals kicking around. It's like in the space of aspect-oriented programming to make this kind of thing easier to express, but that's a 29 or 32 thing. Okay. Existing problems with optional. Construction and assignment from the underlying T or type convertible to a T, inevitable surprises and deep complication in the implementation. Particularly because we want to, for optional tref, make it as safe by default as we can. We have some new technology exposed in the standard library, though, that helps us. We can ask if this conversion would produce a dangling object. This might be this U might be convertible to a T, but it's only convertible because it converted to a whole new object. And now I'm taking the address of it and it's about to vanish. We can detect that and prohibit it. Basically, you'll get a compiler error if you tried to construct that thing. It does rule out some valid use cases, but in ways that it just means you have to write them slightly differently. It's like if you really want to pass something down into a function where that conversion might otherwise be dangling, you can't manage the lifetime, put it in a variable that you own before you call the function so that the lifetime is clear. And then it's on you if the function that you call stashes the address or a reference to this thing that's going to go out of scope eventually. We can't make everything safe, but safe by default was very much a design goal. This overlaps a lot with the design problems for references generally. But the core thing we had, as I alluded to earlier, assign or rebind. I have two cats, Finn, Loki. They're brothers, both orange, share one brain cell. What do these assignments do? What do you expect them to do? It's like I've got an optional cat reference that's empty, and I've got a second one that I've initialized to refer to Finn. It's like, what happens when I assign maybe Finn to maybe cat 1? What happens when I assigned Loki to maybe cat 2? Reasonable people differed. And it's important that it's like very reasonable, very smart people differed about what we should expect for this. It's like, should they be allowed at all? For example, it's like, we've decided that the rebind is the safe semantic that produces the fewest unexpected results. Those two assignments will always rebind so that after those assignments, maybe cat 1 refers to Finn, maybe cat 2 refers to Loki, and that's predictable no matter what the states of those optionals were before those assignments. So you can always reason about what the code is going to do. You don't have to try and figure out, was this engaged or not? Is there some failure mode? Maybe it should throw an exception if it's bound, or just do nothing, or worse in some ways. It's like, turn Finn into Loki because as we've assigned an engaged optional reference. It's like, so the other serious concern is that this makes optional a somewhat non-generic template. The specialization for optional tref is entirely different than optional T. A lot of languages with generic systems don't allow this for good, sound reasons, that you want to be able to reason about the behavior of the generic type. You want to be able to have them all behave the same. We don't want to create another vector bool. Is everyone here familiar with the vector bool problem? It's like, yeah, we specialized in the language, in the library, that vector bool is magically different than vector of anything else, and it turned out to be extremely broken and is a problem to this day. But not quite so broken we can't just delete it. People are actually using it successfully. But the problem is, references in C++ are kind of weird and non-generic to begin with. So the story I tell myself about this in terms of genericity, we're not actually saying I want a tref inside this thing. I want reference semantics. And unfortunately, reference semantics in C++ aren't the same as value semantics, and you have to write things differently. Lots of languages, in fact, I don't think any other language at this point has something that looks like a C++ reference type. We've had extremely good success with them, but also a lot of edge cases that other languages have said, I'll have pointers or something else that's more pointer-like for this category of things. So what were some of the design choices we had to make after just agreeing on this? Because after it's like all this time, it's like I was like, okay, we finally got agreement on this. I just have to write that down and we're done, right? I was wrong. Still took a couple of years of work sorting out all the other parts of the design choices. Big one was, what does make optional do? Now it turns out make optional's mostly been replaced by CTAD. You probably don't actually need to write make optional in your own code anymore. You can just write the conversion from the type to that, and it gets deduced. But make optional always returns an optional T, even specifically if the expression that you're doing over the make optional is reference. Lots of expressions are references. Right? We didn't want to change this. We didn't want to make any other surprises. And it turns out today you can write make optional tref and you'll get an optional t. Falls out from the fact that it's like that's just the deduction from it. Because it's like, you know, we want the expression in make optional, even if it's got a reference, it's like the return value from a function. You don't want to accidentally get an optional reference out of that. You just want your optional t. The way it works today, we don't want to change that. It's kind of unsatisfying, but...
Can you pass a reference wrapper to get the optional t?
No, but you can do some things in that space. It's like it's easier just to actually just write optional tref whatever expression and you get it. You don't need this at this point. We've improved the language that you don't need a lot of these helper functions today. Other important questions, what is the value categories effect on the value function? What should optional tref's value if that optional is an R value, or R value reference? What should you get out of that? We're modeling pointers, which is a reference semantic type. The value category of the optional does not affect at all what you get out of the optional if you dereference it. It's shallow. Otherwise, you could accidentally move from that optional tref. We found some bugs in this space. We'll get to that. Whoops, went one too far. Yeah, const, similar. It's shallow or deep const. We're using shallow const. The language, C++, the language itself, const is shallow. Saying you've got a const thing with reference semantic doesn't tell you anything about what happens when you dereference it. If you want a optional const ref, that's how you spell it. It's like, you can, all good, you just don't get it by default because the optional tref happened to be const. Now, all language references are const, and it doesn't matter where you put the const because you can't rebind them. So it's a little bit of non-uniformity built in. Optional tref just acts more like a pointer, and in fact, there is just a pointer in there. But yeah, optional tref, it's a reference semantic type. It's not a reference. Conditional explicit was another one. It's like, how much do I have to spell things out? I would have preferred actually having explicit everywhere. Too much existing code, too much pain, too much noise. So we pay for it in the library design work. There's a lot more cases where we have to make sure that the conversions were falling into the right constructor that we want. And it's like we've worked it out, but we're conditionally explicit based on what the underlying type's explicitness is for its construction. Like value or was another one. All the choices we had for what should value or return surprised someone, and someone's code was not quite right for it. It's like, if you can't make anyone happy, do the safest thing and come back to things later, which is what I am planning to do. Value or is always now returning a value. So that it's like if you say value or on your tref, you're going to get a T out of it. So, ran out of hours in the day and time before we got to the end of the standard cycle. There are a couple of proposals, including mine, for like generalizing these functions so we could have a value or that actually does way better on all of the things that are kind of optional, like including pointers. What we'd like to be able to do is, like, for example, though, have it return the common reference type or common type of the things under question. So if you say value or reference to this U, it's like, okay, I want the common reference of T and U, it's like as the return value of that. We couldn't say that until fairly recently. We just didn't have the library technology built yet to do it. But it's like, we're doing exactly what optional T does, so your code's not likely to break. In-place T constructions supported, but there's no place to construct in. So we check for dangling, and it's like if the thing is something that we can take the address of that isn't immediately going to evaporate, that's the in-place constructor. We avoid conversions that produce temporaries. We have to avoid some confusion between it's a construction from an optional uref versus an optional T versus a U or a T. It's like there's a long list of constructors for this. The nice thing that it did, we did realize nearly at the end, but just in time, turned out we only needed one assignment though, since we're just copying the pointer. It's like, so principles in reifying the design. We figured out the design, but we want to make this as good as we can. Avoid taking references to temporaries. It's like we check the dangling properties so that it's like if this conversion produced a temporary, that's not good because we take the address of the temporary, it's going to vanish at the end of the expression. It's like everyone here has written this bug, I am sure, because it's so easy to do. We fixed it for a number of cases, in particular range for loops. The temporary that's constructed in a range for loop now lasts over the entire for loop. It used to be that if you had map.thing.something, you could get a temporary and like it would a lot of times appear to work because the compiler wasn't aggressively cleaning things up until it hit production, and it was. So it's like, this rules out some safe cases, but it disallows so many more dangerous cases. We delete the dangling overloads rather than put a requires clause in. So that means that you get an error much sooner, and you don't fall into some other unexpected case in the long list of constructors. We want to tell you that the thing you wrote really doesn't work, not we found a way to make it work. Or the compiler did, really. It's a assignment of an optional tref. It's equivalent to a pointer copy, and all assignments are through the single function. It's nice from standardization. Also turns out to be nice from a compiler optimization point of view. This is very transparent to the compiler. It just does the thing that you'd hope it would do of just copying pointer values around. Mod, of course, the terrible things we learned about in the last session about pointer zap and invalid pointers. Hopefully that'll be fixed soon. It's like, or, The other thing I want to talk about, because it's important for Boost.Optional and the reference implementation, is actually Project Beman. Began last year at C++ Now 2024. I want to be clear, this is, before I get into it, this is not a requirement for standardization. But the important thing about standardizing things, it turns out all the details matter. We have done a lot of things that put into the standard thinking, this is obviously implementable. Sure, the implementation that you've got at home isn't something, is proprietary and has some extra cruft in it or whatever. It's got some extra constructors because of the legacy of everything you've ever done with it. And we've made mistakes this way. It's like, it turns out that it's like, oh yes, that set of constructors is not good. It's easy to make mistakes. It's like, we thought we could make this thing const or make it explicit, but that turns out to cause problems. But it doesn't for your implementation for whatever reason. We really want to see an implementation of the exact thing that's being proposed. And that's one of the things that Project Beman is working on. It means that before something is finally standardized, it's going to be ABI unstable in Project Beman. LAWG says, we've decided we'd prefer this set of names for things. It's not going to have two sets of names. It's going to have just one name. It's going to have the names that are functions that are specified in the standard. You're going to have to change your code to keep up or use an old version, whatever. But the goal is like we can reason about the things in the standard and the things we're planning to put in the standard because we've got something that is exactly that. And then we can easily answer questions like, what if I made this const instead? Like, would that be better? And it's like, I made this const and 5 test cases failed. Okay, maybe that isn't such a good idea then. Or maybe it is and there's something wrong with those tests. But it's like certainly much better than coming back after, or it's like an entire meeting cycle and saying, oh yeah, the thing that you asked me to do, it turned out to be bad. We've got to go back and rediscuss it. But, now, because I'm not smart enough to write standardese without an actual implementation in front of me, I had an existing implementation. And I was able to confirm live at the Tokyo meeting that the proposal to turn optional into a range would work. It's like I put the functions in that were being proposing, took a bunch of test cases that I had for competing range of 0 or 1. They all passed. It was like, yes, this can work. It's like, there's no particular problem with this other than do we want to do it at all or not? There was no technical barrier for doing it, and we decided that it would be better to have just one thing that was optional, like in the standard, than 2 or 3 nearly related ones that fit slightly different use cases. I'm not 1,000% sure that's the best way to standardize things. Other language ecosystems do have more choices, and you actually have to read the docs. Do I want this thing or this thing? Because they're close, but not exactly the same. C++ standard library tends to have one thing that does everything. And sometimes that means it doesn't do everything well. Stood string has way too many things in its interface, and we've always known that. But yeah, the only problem was it with bringing it into Project Beman is that my Scratch framework for doing things was like written around CMake 3.11, and a bunch of things did not port forward cleanly. I was apparently relying on some bugs in CMake at the time, and it's like up the version, and it's like, oh yeah, that doesn't work anymore. And it's like what I was doing to install, for example, never should have worked. Like, it looked like it was working, which is the worst kind of working. It's like, I don't know about you, but it's like, when my code does what I expect, I think I'm done. Ship it. It's like, okay, I got a package install working. Great, okay, move on to other real problems. And it's like, nope. Wasn't working at all properly. It's like, never should have worked. It did by coincidence. Got a lot of help in fixing it up. The other good thing about having this in Project Beman is lots more eyes on it. While we were doing the standard proposals, a lot of people came in and were like, does this satisfy my use case? This looks like it has a problem that I may have run into, and we got a lot of improvements built in. This in particular, the ref stealing bug. So I've got my cat Finn, and I create a cat reference to Finn. Then I have an optional cat. If I move that maybe cat ref to maybe cat, today, Boost.Optional steals the cat and assigns it. This is rather surprising. It's an edge case, corner case, doesn't come up that much, but there are real bugs, because it's like, once I fixed it, found a bunch of places in my own code where, oh yes, this could happen, and it probably is causing this weird crash 1 out of 1,000 times. So, fixed it now. For optional reference, it's not fixed for Boost. It's, I think, fixable, but it might break some existing code. So it's but the core thing was, optional was specified to move the result of operator star. Once we had an optional tref, the value category you got out from operator star was not predictable. It was not always just tref. In particular, an R value optional, a PR value of optional, you can move from that because it's about to expire. So you can enable move semantics from that expiring optional, and it's a win. You don't want to do that for your optional tref because just the fact that the optional is expiring doesn't tell you anything about the thing you're referring to. So yeah, this overload doesn't exist. It's implicit, but this is the core of the problem. This is an actual general principle I've figured out now. Don't try and reason about what you can move. Don't try and think, well, I know what this function does, and I can put the move outside of that. It'll be fine. You can be correct today. You may not be correct tomorrow. It's like operate and move on the things that you know you're entitled to move from, and let those things determine what operations are allowed on a move, and a move is just a cast, on the cast to PR value object. So you want to write stood move star right-hand side, the thing that's coming in, rather than star stood move right-hand side. You don't know if that right-hand side is like good to move from. And you certainly don't know if dereferencing it after you've said it can be moved from is really what you want to say the next time you're coming in with these things. Move semantics are difficult to reason about. The best moves you can write are the ones you don't have to, like return optimization. Like, that's always going to be moved, never write a move there. If you cannot write a move, you're better off. Writing a move is explaining to the compiler something, and that's always risky because you are not necessarily smarter than the compiler. On a good day, you are. Friday afternoon, I'm not. So, okay, as we alluded before, the modal use case, the most common use case for an op is looking up something and failure is not exceptional. Like, we don't want to throw an exception when you found it. You say you didn't find the thing you were looking for. So we want to write a getter for the key type in the map and get an optional reference out for it. We're going to add this for associative containers for C++29. It's not in yet because having both C++26 and 29 in flight is way too confusing for everyone who has to deal with the standard itself. It's 3,000 pages of LaTeX, and it's like, yes, it's in Git, we could branch it, but no, please. Yeah, so P3091, Pablo Halpern, better lookups for map, unordered map, and flat map. It's been reviewed, we couldn't get to it in time for this cycle. It's going to show up fast because it's really easy to write. It's like no implementer has any concerns about this. Just time and motion, though. It's like we were focused on things of much higher value. It's all the reviews for like SIMD, the MD span, executors, like high value, important things that we all wanted just took priority. Like only so many hours in the day. But best time to get things, simple things in is really early. So I've got now a list of things I want to start getting ready for 29. So as soon as the gate opens, like, here's 3 things. They're all trivial. Let's just do them.
Please use the microphone. We cannot hear it for the recording.
Sorry.
In the audience, thank you.
Okay, well, hold. It's like,
yeah.
Since this was the we had reached the last slide. So it's like, but yeah, questions. Remember, question starts with who, what, when, where, how, why. Goes up at the end. More of a comment than a question. Let's hold them for a moment. So, questions?
Sorry for the interruption.
No.
On that last slide, it's vector arrays and that kind of stuff included in
Well,
getting
vector
a
doesn't
get?
have the lookup problem.
Well, it does. It doesn't contain infinite elements, right? Like the index has to be between 0 and size.
Oh, okay. It's like that hasn't been proposed.
Okay.
It's like you could be, and it's like honestly that you could write that almost as efficiently as we could. We can do it more efficiently inside the containers than you can outside, significantly so. I mean, as significantly as a 2 or 3 line function is going to be. But getting these into the interface, into the as members of the associative containers is a win over like wrapping up checking the index in a vector. But
yeah, I mean it as a replacement for at, right? Which
Yeah.
you have, for example, in maps as well. You have it in vector, so there's a sense of symmetry there as well.
You
But
could
yeah.
write essentially the same code, and it would be exactly as efficient as if we put it inside
I
the
see.
container.
I understand.
This is not. It's strictly more efficient if we do it inside the container.
I understand.
So,
Yeah. Cool. Thank you. Thanks for the talk today, and thanks for all your hard work dealing with all the non-intuitive cases over there. There was a question earlier about stud reference wrapper. I didn't quite get the answer. How would it differ, optional of stud reference wrapper
it's
versus...
very similar. Reference wrapper, its original design was part of the DSL for dealing with tuples. It's got some peculiarities in its API. It's like you can do most of what we're talking about doing here with having an optional over a reference wrapper of T. And reference wrapper of T really does just have a pointer inside it. It doesn't do all the things that we would like to do about not dangling, though. Because when we wrote it, that wasn't a concern. And we're basically, it's like, having reference wrapper and its semantics was at least a plus, and it's like, look, we already have one of these in the standard. Some people must like these semantics, but using it is painful. It's and it's like, I've done it. There were some versions of this that had some interop with reference wrapper and some specializations. It just caused headaches with finding the right overload. It made the overload set too large, and the compiler kept saying, I want to use this constructor. And I'm like, no, you don't want to use that constructor. It's like, well, I don't want you to use that constructor. I can now see why you want to use that constructor.
I see. So
but yeah.
It comes with some strings attached, but possibly can be used as a Pullman's polyfill until
yeah, although it's like I have not pushed this is 1.0 in Beman, only because I'm not happy with the docs right now. This is more a problem with Doxygen than Doxygen thinks that conditional explicits are functions and wants to document them as functions. And I'm like, no, you're getting the wrong part of the function. But it's stable and done, so it could be. One of the challenges is, though, that your optional T and optional Tref have to go together. In some cases, they need to interoperate and know about each other. Or you get weird conversion problems. In particular with the monadic functions. If you're applying a optional Tref returning function as the transform on your optional T, you want them to do the right thing. And like the stud one would say no. It's like TL optional doesn't have some of the other semantics, and it's like you want a coherent set of these. But this Beman optional is a good drop-in replacement, and I know Live Standard C++ already has this implemented, like in trunk. So this is going to show up quickly.
Awesome. Thank you. Mm-hmm.
Hi, thank you. I was wondering about consts on these optional references. It seems like we could have an optional const reference or a const optional reference, or const both places. As far as for users, is there ones we recommend against?
Okay, it's like it works just like pointers.
Okay, so
your const pointer can point to a mutable thing.
Do they all have like use cases, or there's ones we would just
okay. I never want this to point anywhere else than where I said it was pointing.
Okay, so they all may come up.
Yeah, it's like it may not be your use case, but it's someone's.
Thank you.
Thank you for the nice talk. Was it considered to have an alias to optional_ref to create an optional reference? So this would kind of removes the naming problem with make optional, so you can then say make optional ref.
Yes, but that mostly that wouldn't have solved the problem that I really want, where I want to fix this for variant.
Okay.
Because it's like I ran into this problem. It's like as soon as C++17 came out, you can have a reference in a tuple. You can't have a reference in a variant, which means that you can't use a tuple as a heterogeneous container because you'd want to convert the tref uref of tuple to a variant tref uref, and you can't.
Okay.
So, it's nowhere near done yet, but we've got agreement in principle on what variant with a reference in it should look like now. It's like we don't know if it's actually implementable given the current existing variants, but that's the standard library authors seem to actually be more convinced that it was possible than I was. So I'm like, okay, if you think it can be done, that's good.
Okay, good luck.
Yeah.
Hi, nice talk. You mentioned that optional tref contains a pointer to a t inside
Yep.
of it. So what happens if t is bool?
Oh, yeah, it's like, we try and be careful about that. No, it's like, yes, you can do that, and there's some test cases for it. Like internally, we're try and be careful about checking that we're null and not having just implicit, 'cause you never, as a user of optional tref, you never see the pointer. So we just have to be careful about not using textual bool, convertible to bool to govern anything.
I guess I was kind of asking, like, did you implement that specialization, or
It's like
or are you just doing the proxy thing that like bitset does?
Basically, if you're careful, you don't have to do anything special for it. You just have to write the code like longhand. It's like, compare against null pointer, not just if pointer, or if deref pointer, or anything like that.
Thanks.
Thank you, great talk. Glad I won't have to type std optional of a std reference wrapper. If you could go back to slide 15.
Maybe? Nope, too far. 11, 12, 13, 14. Okay, yep.
So when you're doing the optional as a range, is this a bug in your slideware where it's auto as opposed to auto ref? Because normally when you iterate over
Oh,
a
yeah,
range,
it's like slideware. So it's like, it compiles, because I compile my slides, but yeah, it's like, no, that should be like an lref, like to get the,
so there's not
correct
different
deduced
semantics when you're iterating over an optional of a reference.
It works just like other ranges. That should be an auto ampersand L to get, it's like to make it a universal, not a R value, like the template rules, not the, yes.
Okay, awesome,
So-
thank you.
Yeah, I did not mean to accidentally copy the logger there. Yeah, I think that would have ended up copying the logger. It's like, the test case behind this, the logger was just an empty struct, so.
This is more of a sanity check question, but in your swap implementation, it will rebind both optionals.
Yes.
Okay.
It's underneath the hood, it's just a pointer swap. But yeah. Let's see. Let's go forward. I think we're. Any comments? Thank you.